Okay, so first of all, we introduce Coulomb's law at the very beginning, right? So if you have 2-point charges, let's say Q small and Q capital, of course they interact. And this is basically universal law, Coulomb's law. All right. And then we introduced, based on this Coulomb's law, the idea of the electric field. So in order to measure the electric field, you need to take small positive probe charge, position it in this electrical order, measure the force acting on that charge, probe charge, and divide it by the value of the probe charge. So that's how we define the electric field. Let me frame it because it's important. So that's how we define the electric field. Then recently, a few classes ago, we started, it's difficult to deal with vectors, so we decided let's try to develop an alternative approach to solve problems. Instead of force, electrical force, we decided to introduce U, which is potential energy. Potential energy, right? And potential energy is the energy of interactions. There must be at least 2 objects interacting. So we decided, so let's look first at the capacitor. Let's say plus, wait, it's too small, let me make it bigger. Let's say if you have a capacitor, let me start with minus, and here you have plus. We introduce coordinate system, right? This is S, this is S equals 0, this is S. If you have a charge over here of value Q, then the potential energy in this case, do you remember the expression for the potential energy on the charge inside of a capacitor? QES, force QE, right? QE, and times the position of the charge. Of course, that will be given in the formula sheet, right? So let me frame this as well. So it's potential energy over a charge inside of a capacitor. In the second, potential energy of 2-point charges. So if you have charge, let's say Q and Q small at a distance R, then the potential energy. This expression you should remember probably. What's the expression for this potential energy? It's basically like Coulomb's law, but downstairs the first power of R, right? So it will be K. Q small, Q capital divided by the first power of R. So that's the potential energy when you have 2-point charges, and of course they interact. Then, all right. So let me separate this. And now, if you have charge exposed to field, how can we find force acting on the charge? Do you remember? We've used that formula quite a lot. It should be at the top of your head. Yeah, I know you do. Charge times the value of the electric field at the point where the charge is. So you just need to solve it for F, right? It will be just QE. QE. F equals Q times the value of the electric field. Okay, I can put the vector for it, right? It's one of the fundamental equations. Actually, it's an equation which we will add closer to the end of the semester to a set of Maxwell's equations. So that's the force on the charge which is exposed to electric field. Right. Okay. Electric potential here. I would review the electric potential, but I told you the electric potential stuff is not going to be on the exam. That's why here I have like a gap. It doesn't look aesthetically good, but so all right. Next, let me separate it this way, right? So next, Gauss's law. We introduce Gauss's law. So if you have a bunch of charges, right? All right. Q1, Q2, Q3, Q4, Q5. Some of them 5, some of them positive, some of them negative, right? It doesn't matter. And in order to apply Gauss's law, first of all, of course, you have to pick a Gaussian surface, right? It's just an imaginary surface, right? Pure mathematical idea. And that surface must be a closed surface, right? It's extremely important. That a surface must be a closed surface. So let me pick it over here. So that's my, let's say, Gaussian surface. And then, of course, Gauss's law, fundamental law in physics, integral over the closed surface, E dot dA equals to Q enclosed over epsilon naught, right? So, your left-hand side, on the left-hand side, what's the name of that quantity on the left-hand side? Do you remember? On the left-hand side, that integral. What's the name of that quantity? Yeah, flux, I want to say flux capacitor. I watched too many times Back to the Future. I need to stop doing it. Of course, yeah, this is just a flux. Okay, I can write it here. So F phi sub E, electrical flux. That left-hand side is just electrical flux. So if the question is about finding the electrical flux, then it's trivial. You just count charges divided by epsilon naught, and that will be the amount of flux. And the idea of the flux, in simple words, is just basically the number of electric field lines crossing a certain surface. In this case, our Gaussian surface, right? So if you calculate this, this will give us number of electric field lines crossing this surface. Flux is positive. What does it mean? It means that, let's say, electric field lines leaving this surface. Flux is negative. What it means? What does it mean? It means that electric field line going into the surface, right? That's what positive or negative flux mean. Okay, we will practice that. In this case, of course, Q enclosed will be Q1 plus Q2 plus Q3. These charges outside, forget about them, because they're not going to contribute anything to the electrical flux, because the electric field lines over here they will enter, and over here they will leave the surface, giving us the same amount of positive and negative flux, overall 0. Okay, so now let me separate it this way. And now let me also mention electric flux. Electric flux, so it's a phi sub E, because when we get to the magnetism, of course, we're going to use here a letter P, which stands for the magnetic flux. So in general, of course, it is integral of E dot dA, but in a special case, when you have flat surface and uniform electric field, we can just simplify it, and it will be just E dot A. A, area vector. Don't forget it. And don't ask me on the quiz, because I heard on the quiz, what is the area vector? We've practiced it, right? So refresh it. Right, now. Okay, so the last piece, and then we'll start looking at the problems, because after that, not much to discuss. Conductors. Then we introduce a bunch of properties of conductors. And conductors, in which state? What's the name of the state? We discuss conductors every time. Electrostatic equilibrium, right? Electrostatic equilibrium. And let me write in electrostatic equilibrium. Again, guys, if something not clear in terms of my handwriting, quickly say something, scream something, and I will clarify. Because I know if students find it different, to see the difference between my N and U, for example. Right, so let's assume that we have a piece of a conductor in electrostatic equilibrium, right? So first, major property of piece of a conductor, piece of metal, major property. It has tons of free electrons. The rest of the properties follows from that major property. Tons of free electrons. Then next most important property. What's the value of the electric field inside of a conductor? Zero. It doesn't matter what you try to do with this conductor. You can try to expose it to a different strong or weak electric field. Electrons will be running and they will organize themselves in a such way so that the electric field inside of the conductor is zero. Right? Of course, it will take some time, maybe nanosecond, maybe microsecond, to achieve that state, but eventually, electric field inside of a conductor must be zero. Then, let's say you dump some amount, let's say, of positive charge on this conductor. Where is that charge going to be? On the outside surface. Inside of the conductor, it's impossible to have excess charge. It doesn't mean that there is no charge in there, but we have equal amount of positive and negative charges. Any excess charge must be on the outer surface. Right? Any excess charge. Then, electric field outside. What can you tell about the electric field outside? Any special feature of the electric field outside? Features? Your lab work.
I missed the question.
Okay, so if you have a piece of a conductor, let's say it's charged, right? So what can you tell about the electric field outside of that piece of a conductor? Anything special?
Is it the opposite?
No, not the opposite, right? It's you in your first lab report. You try to recall your picture. Okay, help. It's perpendicular. Do you remember your electrodes in the lab report?
Yeah.
In that picture, and your electric field lines, they were perpendicular. Okay, give or take, right? Because within your experimental error. But of course, ideally, they must be perpendicular, right? So, electric field outside is perpendicular. No matter what you do. Again, in electrostatic equilibrium. Of course, before conductor reaches that state, it can be anything. So, that's electric field outside. And so, I think I mentioned everything. Yeah. Another important feature, we will get there probably in a class. And of course, this is piece of metal. This is piece of metal. Right. Probably I should have written also over here. So that was our force approach, right? Which we used to solve problems, right? Motion of some charges in electric field and so on. This is energy approach, which can be used, right? So when we used force approach, which fundamental law every time we used? When we used a force approach?
Newton's second law.
Newton's second law, you will find acceleration, and then once you know acceleration, and if the acceleration is constant, you can use kinematic equations. Over here in the energy approach, which fundamental law here, every time we use? Conservation of mechanical energy, right? So here, let me write underneath. Initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. It's a conservation of mechanical energy. I just wanted to fill this void, right, with something, in order to make it look better. Right. Conservation of mechanical energy. And on the exam, because you have two approaches, sometimes both approaches are equally, I don't want to say simple, right? Equally, let's say simple, right? sometimes energy approach is much easier than a force approach, right? So on the exam, of course, I will give you a hint, right? Use energy approach or conservation of mechanical energy, or use force approach, right? So that, because sometimes it's just making a decision which approach to take, it can be it can be painful, right? Okay, so of course on the exam I will tell you. Let me check. I think I mentioned everything. Yeah. Okay, so now let's start with problems. I will keep that on the board, and I need to move the camera. So, problem, again, it's very similar to what you had, I think, in your homework. I think a couple of years ago, I gave this problem on the first midterm exam. So let me put a new bullet. And situation is quite simple. You have a charged object of mass, certain mass. You attach it to the cord, suspended from the ceiling. You will expose the charge to the uniform magnetic field, and of course the charge will be deflected by a certain angle, right? So we'll have to find the just the charge of that object. So I will probably draw the picture first. So that's my ceiling. That's my cord. That is the object of mass m. So we have mass is 5 grams. Okay, of course we have to convert it to kilograms. 10 to the power of minus 3. All right, then of course you can easily measure this angle theta. Let's say theta is 20 degrees. And everything is exposed to uniform electric field. Yes. Yes. Right. So this is a uniform electric field. So we have electric field over value of 100,000. Don't forget about the units at the very end, at least, when you write your final answer on the exam. Don't forget about units, right? Because you need to tell people what you actually measure or calculate. Electric field, newtons per coulombs. And yeah, so we need to find the charge on the of this ball. Okay. Again, it's very similar to what you had in your homework. First, can you tell me immediately, what is the sign of this charge? Is this charge positive or negative? You think positive? What do you think? Positive? Yeah, why?
You have the field going
Yeah.
one way, so that be positive, negative.
Exactly. Since our object is displaced that way, right? It means there must be force acting that way, and of course that is the only force which can act in that way is the electrical force, right? And of course the electrical force F equals QE. Direction of the electric field that way. Charge is positive, so force must be also in that way. Right. So so charge must be positive. Then, which fundamental law are we going to use to start solving this problem, to start discussing this problem? Which fundamental law? Huh? What? Coulomb's law will be used, but that will be later on, right? So when we start picking up some details, right? But something like, first you need to decide, like in general, we're going that way, right? What? Okay, exactly, right? So not electrostatic equilibrium, it's just from physics 1 static equilibrium, right? But static equilibrium is just a consequence of Newton's second law. Newton's second law, right? It's a law which is capable of describing motion of any classical system, right? As I keep saying, it's something, it's not just F equals ma, it's a tremendous, right? You can grab any mechanical system, and if you want to describe motion of that system, use Newton's second law, and you should be able theoretically to do it. So, motion of any system. Here, we don't have motion. It's a static situation. But again, no motion, as I said many times, it's just a special case of motion, right? No motion, it's a special case of motion. Velocity 0, acceleration 0, it's a special case, right? So, fundamentally, we need to start from the Newton's second law, which is, of course, in general, sum of the forces equals mass times acceleration. Mass, of course, of our object. That's our system which we want to describe. And so, acceleration is 0, not just constant, right? 0, because system doesn't move, right? Don't use acceleration due to gravity. Acceleration due to gravity has nothing to do with this. Acceleration due to gravity is of this object, right? This object moves with g. Here we don't have acceleration. So acceleration equals 0. So as a result, we're getting what you said, right? So static equilibrium, right? So we just need to balance all forces acting on the system. All right, so that is our fundamental beginning. How many equations of this inside of this equation? How many equations inside of this equation? 2. We have two-dimensional system, right? Of course, now let me introduce coordinate system, right? Because we're dealing with vectors. We are using this force approach. So I need to introduce coordinate system. When you use energy approach, yeah, you can skip introducing coordinate system, but here it's a must. Okay, I will do it this way. Y, X. Again, if something not clear during the discussions, tell me immediately. Okay, so now next step. Basically, we need to complete free body diagram. We need to draw all the forces acting on the object, and then we need to balance them all. So first force. I'm not asking you, it's a physics 1, right? Force of gravity, it's going straight down, mg, right? Then, electrical force, of course, to the right, yeah, to your right, must be. So that is F electric. What? Something?
No, we figured it out.
Good. And then, of course, there must be tension along the chord, away from the object. Physics 1. Right, so which way I label it? Ft? Yeah, F sub t. F sub t. So now, 3 forces. So we need to balance them, of course, in the x and y direction. Let me start with which direction? Okay, let's start with the y. Sum of the forces in the y direction equals 0. Right, and sum of the forces in the x direction must be equal to 0. So that is a system of 2 equations. We just need to write them down explicitly with all details, and from there you should be able to find everything. So, in the y direction, equation. What will be the equation in the y direction? We'll just use this angle also theta, the same angle as this one. There. Equal and, so, okay, I'm not asking you, right? First force in the positive y direction, Ft times cosine of theta, right? And again, before the exam, actually even on the formula sheet, there is a triangle. If you don't remember which function to use, cosine or sine, check that triangle, right? It's given, because I know you still, even in physics 2, students struggle with this sine and cosine functions. Okay, so it will be Ft times cosine of theta. Is it positive? Is this contribution positive or negative to the equation? Positive, because this component acts in the positive y direction. And of course, mg is negative, so it's a minus mg, and these two forces must balance each other out, right? Then, in the x direction, electric force, positive x direction, so I will just write F sub E, and a component of this tension, this component. Positive, negative? Negative, because it points in the negative x direction. So it must go into the equation with minus. So it will be minus Ft times sine theta. And these two forces also must balance each other, or must cancel each other. Okay. So now, next step. You started talking about Coulomb's law, but do we need the Coulomb's law here? So, electric force equals to what? What is given? Electric field is given, right? So that force must be written in terms of the electric field. Right? So it will be what? Q times E. Q times E. The electric force equals Q times E. Okay, so now we have a system of these two equations. How many unknowns are there in this system? Two. Tension force, and what else?
Q.
And the charge here, Q. That's what we need to find, right? That's what we need. Okay, so from the mathematical point of view, system is solvable, right? Two equations, two unknowns. Again, at this point, as I keep saying, physics is over. Now it's just algebra. You just need to solve a system of two equations with two unknowns. Two algebraic equations, which should be quite simple, right? So now let's do it. Let's get from the first equation, tension Ft will be equal to mg divided by cosine of angle. Again, if something not clear, ask me immediately, right? And we can plug it into our second equation, right? So we'll plug it into this. So, and I will write, so QE minus, instead of Ft, it will be mg cosine theta times sine theta equals 0. So I just plug from the first equation tension. And instead of Fe, I have QE. I just rewrote second equation with this, not substitution, just what we found. Okay, so now how many unknowns we have? Only one. Now it's only one, so only charge. The rest is known, which is eliminated tension. So from here you can get charge immediately. Of course, this goes to that side with plus. So divided by the value of the electric field, mg E, I will of course take outside, and sine over cosine tangent, it's a tangent function, of course, times tangent theta. Constants, I know here mass is given, right? So we're not dealing with electrons or protons, but those constants like epsilon naught, k, charge of an electron or proton, their masses, of course, will be given in the formula sheet. Right, again, don't forget that you have to use kilograms. Okay, I'm not plugging this value, so we'll just write down the answer. It will be 1.78, okay, 366, whatever, times 10 to the power of minus 7 units of Coulomb, right? Don't forget to write at the very end of this units. I'm not going to solve problems like motion of a charge in capacitor using the force approach. You just use this formula to find force, apply Newton's second law, find acceleration. If acceleration is constant, you can use kinematic equations. You can find any kinematic parameters you want, like velocity, position, time. Okay, any questions on this? Yeah, it's basically one of your homework problems. Extremely similar problem you had. Now, a few conceptual questions, and then we will move to another problem. So we have, let's say we have a piece of a conductor. So let's say I have charge -5 coulomb. Here I have charge +2 coulomb. So what will be the electric field inside of the conductor? 0, right? Never forget that, right? Never forget that. And again, now since we introduced conductors, read the problem properly. If it says a non-conducting material, it means just some object filled with charges, for example, but it's not a conductor, right? But if a problem says it is a conductor or metal, yeah, of course you need to carefully recall all those properties and use them, right, if they needed to solve the problem. So read, if it's a non-conducting material, you cannot use those properties of conductors, because I see every semester some students would forget about that. So it's only true if you have metals. So of course, yeah, electric field will be 0. Of course, the electrons will run around. Here, of course, I'm sure that we will have some bunch of electrons on this surface, right? A bunch of positive charges will be on this surface, right? Of course, they will be distributed in a complicated way, trying to make electric field inside 0. Okay, good. Right. So now, I was thinking about something else. Okay, now let's do this problem, like we did in the lecture. So I'll put another bullet. So let's say we have a conductor. So let's say that is a conductor. And let's say we have hole. Right, so that is the hole. Right, so that is the material. And let's just give me some numbers, right? So total charge of a conductor. Give me some number.
7.
Again, use 7, right? You will come with 8, right? I asked that guy. I still remember in the lecture, activist. Now I'm asking guys, right? I'm not asking girls, right? I remember you gave me a bunch of negative numbers, right? What?
1.
Oh, give me something more. 3. Okay. 31. Okay? So Q total 31. So I combine in a democratic way. 31 coulombs. So that's the total charge in a conductor of this conductor. Now give me a charge inside of that hole. Yes, from this side. So any number for the charge inside of this hole. 11. Now you like it. Right, okay. Q H 11 coulombs. Right. So now this time you're positive side. So okay, so now you remember, right? The question, typical question, standard question. So what's the charge on the inner surface? So we need to find Q on an interior surface. Of course, you can answer me immediately. So what will be the net charge on the interior surface? Do you remember? Huh? What?
0.
No. Okay, in simple words, look. This positive charge, right? This is a conductor. The major property of a conductor, it has tons of free electrons. Those free electrons can move. So when those electrons see this positive charge, what will be their response? Of course they will move. You remember, opposite charges attract. Of course, negative charges will be running towards this positive charge, and of course they will reside, they will end, their life will end, or they will live over here, right, or whatever, near this interior surface, inner surface, right? It's in simple words. In more sophisticated words, these electrons bravely will attack this positive charge, trying to make the electric field inside zero. That's their goal, right? Electrons will keep moving to this side, and they will distribute themselves around this surface, trying to make electric field inside zero. So let me write here. So here on the inner surface, we're going to have Q inner equals to minus 11 coulombs. Of course, I'm not going to ask, yeah.
Question. So the total charge that you derive, is that the charge that's outside?
No. You mean outside, on this outside surface?
Yeah.
We cannot tell that exactly. We need to do the next step. Right now, we can only, I can bet all my money that minus 11 coulomb will be on the inner surface. I can prove it. I can use, like what we did in the lecture, use Gauss's law. If you pick Gauss's law over here, just below this inner surface, what will be the electric flux through that surface? Zero, because electric field inside is zero, right? Flux is zero, and according to the Gauss's law, if flux is zero, Q enclosed must be zero, right? Q enclosed must be zero. But we know inside of the hole there is a plus 11 charge. It means that there must be somewhere minus 11 charge. And of course, that minus can be only on this interior surface, because that's the only area left. Because we pick Gaussian surface just below that surface. So that's the not justification, it's a proof, right? When you use Gauss's law, it's a proof. But of course, on the exam, if you just write the right answer, of course, we will accept it. Okay, so Q inner, of course, must be opposite and exactly the same in absolute value. Distribution of this charge, of course, will be complicated, most likely, right? But I can tell that the total charge on the inner surface must be minus 11. Now, about the outside. Outside, now Q outside, on the outside surface. So, we know that this piece of a conductor is isolated, right? Charge is not leaking, there is no escape for the electrons. So if we dumped 31 coulombs into this conductor, that amount of charge will be throughout the whole life of this piece of a conductor, right? Every time, if you add all the charges inside of a conductor, this is not part of a conductor, inside of a conductor, there must be 31 coulombs. So it means that number is constant. Then, where is that excess charge can be inside of a conductor? Inside is impossible, right? So it can be only on these surfaces. Outer surface, interior surface. There are only two places. Inside of a conductor, it's impossible to have excess charge. All this charge is excess charge. So I can write conservation of charge. Conservation of charge. And I will write of the conductor. This charge inside of the hole is not part of the conductor. Okay, so I can write, you know what, let me move to this side because I'm getting lower, too low. All right, so I can write Q total must be equal to Q inner plus Q, the total charge on the outer surface. This we know, and that is unknown. Just conservation of charge, you can get what will be on the outer surface immediately, right? It's simple algebra. We've done very similar in the lecture, very similar problem. So from here, Q on the outer surface will be equal to Q total minus Q. Okay, I use Q small here, Q capital. Okay, you understand. Okay, let me fix that quickly to avoid any confusions. Q. Right, so now we can write total 31 coulombs minus from the expression the value on the value of the total charge on this surface minus, so we have two minuses. Well, 2 minus 11 coulomb, so minus and minus is plus, yeah.
Is there any difference in the positive and uppercase and lowercase q's? Or
No.
Okay.
It just, since I started using lowercase, right, and then I switched suddenly to uppercase and I realized, yeah, I should be consistent, right? That's why I switched. Right, and so we'll have what? 31 plus 11, 42. I thought we would subtract it, and I like it now. So it will be, so we have to add 42. Okay, let me write plus. Emphasize on the plus 42 coulombs. So basically, what does it mean? That electrons from here run to the inner surface, leaving more positive charge on the outer surface. In the hole.
Yeah, in the hole. So that was positive, but it became negative.
No. This is positive, but on the inner surface, of course, there will be a charge with the opposite sign every time.
Okay, so that's the current.
Of course, in simple words, as I said, it's just a force of attraction. Electrons will be either attracted if there is a positive in the hole, positive charge in the hole, and of course, electrons will be repelled and they will run away if there will be a negative charge inside of that hole, right? If electrons run away, of course, they will leave a positive charge on the inner surface. Only electrons move. Positive charges cannot move, right? Because those are inside or in the nuclei. Okay. It's a simple question, but from time to time I like to ask this, right, just to check conservation of charge, right, and simple understanding of processes inside of a conductor. Now, okay, now let's play around with the flux. Now, there is a very strong impact on me and the movie Back to the Future. Again, I pronounce flux and immediately, you know what my association. Okay, I will erase probably this part so that I don't have to move the camera. So let's say we have, again, it's another more or less conceptual question. So let's say we have a charge, Q, and positive. And let me pick this closed surface. Right, so let's say this is some closed surface, a cylinder. Right. What will be the net flux through this closed surface? Through this closed surface, what will be the net flux? Not next flux. What will be the net flux? Huh? 0? Yeah. It will be 0, because in this case, again, we will just use Gauss's law. If the question about finding flux, the question is trivial. If you see, if you see charges, since inside of this closed surface, there are no any charges, right? So of course, from the Gauss's law, immediately you can write. So from the Gauss's law, electric flux, which is the integral dot dA equals Q enclosed or epsilon naught, right? So flux must be equal to Q enclosed divided by epsilon naught. So since this is 0, so the flux is 0.